Pessoal, boa noite a todos. É um prazer enorme estar aqui com vocês hoje à noite novamente para mais uma atividade promovida pela Associação Brasileira de Mecânica dos Solos. E hoje eu diria assim que é uma dessas noites memoráveis, porque nós temos o prazer de ter conosco um dos grandes especialistas internacionais na área de barragens e, em particular, na área de rejeitos de mineração, lidando com problemas associados à liquefação de solos e de rejeitos. É o Dr. Mike Jefferies. Ele teve a generosidade de aceitar o nosso convite e vai ser muito interessante tê-lo conosco essa noite. O Mike, eu vou apresentar ele para vocês na sequência. Eu reputaria como uma das pessoas com uma trajetória muito especial, muito particular, porque ele faz como ninguém uma ponte entre teoria e prática. Ele trabalha como consultor geotécnico, mas tem uma sólida formação teórica, tendo inclusive desenvolvido um modelo constitutivo que é utilizado hoje de forma corrente em projeto de fundações de barragens de rejeito, que é o modelo North End. Então vai ser muito interessante ouvi-lo. Eu agradeço a presença de todos vocês e eu vou agora trocar de língua, passar para o inglês, para poder fazer a apresentação do nosso convidado. Mike, good night. It's my pleasure, on behalf of the Brazilian Geotechnical Society, to welcome to this webinar in Brazil. We all recognize you as one of the global experts on soil liquefaction, and this is a key issue related to the design of dams and to dam safety, which is your subject tonight. Regardless to say, the design of tailing dams is a critical subject to the Brazilian community, given the impact of commodities on the Brazilian economy. So we are very excited about hearing you tonight. Before formally introducing you, I just would like to make a comment, a remind. As you probably know, as you probably are aware of, ISSMGE has launched a new technical committee, a technical committee on tailing and mine waste, TC221. And this committee, the board members of this committee, that's led by Professor Ramon Verdugo, has prepared a questionnaire with 6 quick key questions related to the design of tailing dams. These questions have been uploaded on the website of the Brazilian Society of BMS, and I would like to see if you can reply to this. It would be very interesting to see your views about these posted questions. So go there and fill them. There's going to be a broad discussion on that subject later on. As for the presentation, Mike is going to deliver a slightly longer lecture, including all aspects related to this discussion, to the discussion of dam safety. And then we decided that questions can be made on a written form and will be answered by him later on, okay? So another important information is that you've got one of his papers that is available at the ABMS channel, so you can just download the paper from there. But there's going to be also a written version of this lecture that will be published as a special paper at Soils and Rocks, the Brazilian geotechnical publication, right? So now, coming to Mike, he's a registered Canadian professional engineer with a broad background of some 45 years in offshore plataforms, dams, and ground improvement. Strongly influenced on his early years by professors Bob Gibson, Alan Bishop, and Peter Roth. Quite a team. Mike has pursued an interest in theoretical soil mechanics, despite working as a consulting engineer, which produced the general form of critical state theory. As I was mentioning before, Mike has the ability of making this relation between theory and practice, bridging theory and practice with his contributions. A keynote speaker or author of international conferences on liquefaction, hydraulic fuel construction, engineering mechanics, and offshore platforms. Mike has published some 80 papers, which had attracted about 7,000 citations, and is the co-author of the influential book, Soil Liquefaction, A Critical State Approach. That's together with a dear friend, Ken Bean. Mike was an invited contributor to Geotechnique, the Canadian Geotechnical Society's fall 2012 Cross-Canadian Lecturer, presented the 2014 Silky Lecture, and gave the 2017 Jenkins Lecture. He was awarded a Telford Premium for geotechnical research in 2017. Mike, again, it's a privilege and it's a pleasure to have you here. So now you're in charge. The floor is yours. Thanks for accepting our invitation.
Well, thank you very much for that kind introduction, and good evening, everybody. This is it's going to be an interesting story, and it's about 65 slides, so there's a fair bit to go through. What I'm trying to accomplish this evening is I'm going to touch on 3 points in terms of the material I'm going to present. I'm going to go through the history of where these ideas come from and how they have evolved. And this has happened over really 3 periods. And if you see there, the first date that's going to come up is 1885. The original ideas came from the Victorians. This is quite an old subject. And a body of information came together. And around 1955, it was fairly clear the key aspects of soil behavior. So the following 30 years, I've dated from 1960 to 1990, the trends we saw in testing was pulled together into a proper theoretical framework, and that also involved evolution of test methods. But at 1990, this was very much, shall I say, there were practical aspects, but it was to some extent a university exercise, because you couldn't really compute. You couldn't do a stress analysis with this theory. That changed over the period from 1995 to 2015, which saw movement of these ideas into finite element software. And the real key point, and perhaps the reason this is new to a lot of you listening to this evening, it was only around 2014 that the stuff became available in commercial platforms that consulting engineers could use. So even though the subject is 100 plus years old, really it's only in the last 5 years that those of us who earn our living by consulting engineering have something to work with. So perhaps that's why it's new. But anyway, I'm going to go through the history because I think it's important to understand there's a range of contributors. This is not the work of one engineer. It's not the work of one university. It's a whole body of people who have contributed to this. And of course, as you guys have this interest in dam safety, so I will illustrate the application to dam safety and this business of sudden liquefaction for dams apparently showing no signs of distress. I'm going to look at failure by load increase, and I'm going to look at failure by pore pressure increase or decrease confining stress. Look at 2 cases. And I will show 2 examples. And one of the criticisms, particularly out in New Zealand, of critical state theory is it's very much a theory anchored to soils without any structure in them. But it's not very difficult to extend the theory to include structure. So I'm going to show you an example of how the theory works with the residual soils. And the particular motivation in suggesting this talk was I I think it's very important to give people the opportunity to raise questions. You know, you guys have seen North American engineers coming down to talk about your dams, but my perception, and I may be wrong, but my perception, it's been a one-way conversation. So I very much wanted to give you guys the opportunity to say, hey, Mike, this doesn't make sense, or perhaps, yeah, have you considered this? So this is very much, this talk is a briefing to perhaps surface the questions you may have. So the interactions to come on the question answers is really the key here, or what we're trying to achieve. Okay, so much for the structure of the talk. Let's get on with the talk. The origin really of critical state theory goes back to the Industrial Revolution. And when the Industrial Revolution started, 1850 or whatever, you saw quite a large migration of people from the land into cities. And the first thing you need to do when that happens is you need to provide a water supply. You think of your fellow civil engineers of 100 years ago. They didn't have D10 bulldozers. They didn't have 200-ton dump trucks. But what they did have was pumps. And hydraulic fill construction became a usual method of building dams. The slide you see in front of you, if you look carefully down here, you can see the date. This is 1912. This is actually one of the water supply dams for the city of Vancouver in the west coast of Canada, and it's still in service today. And this photo here illustrates the construction. You have on the left what they call rock fill. In mining, we'd call that our starter dike. And you can see the spigoting. And then you have the decant in the middle, and you have this magically self-forming dam. And this was a standard way of building dams in the period of, say, 1890 to even 1940. But what was discovered relatively early on, and then you see another dam here on the photo on the left-hand side, you see, I notice the site truck is a horse and buggy. And there we have our spigoting. And what happens very often was these dams would suddenly collapse. And this is the oldest slide I have ever seen of a liquefaction. It's a liquefaction event from 1918 in California. And if you look at the literature of the American Society of Civil Engineers of this period, it was that a dam had liquefied was unremarkable. They persevered with building dams this way because they cost half the price of trying to do it with placing fill any other way. But they had a lot of failures. And there was a particular engineer, we're going to see the dam in a second, but when the Americans looked, and this was very much the US Army Corps of Engineers who led this, they actually looked to a chap called Reynolds. If you remember your hydraulics lectures, you have the Reynolds number. Well, it's the same Reynolds. And what Reynolds did was he said, well, if you look at soil particles, I'm circling them here, and if it's sand, you can see them with a microscope or almost with the naked eye. You can see individual particles. What Reynolds said was, well, let me idealize those particles as steel spheres. And that we see here and here. And you can arrange steel spheres in different packings. And the packing you see on the left is a face-centered cubic array, and that is the loosest theoretical packing for steel spheres of equal size. Over here is the densest possible packing. That's a body-centered cubic array. And what Reynolds observed was any deformation requires those spheres to displace. On the left-hand side, they will tend to fall into the holes between the spheres. On the right-hand side, they must expand or move apart to allow deformation to occur. So what we have from this very simple idealization is the notion that soil behavior is going to involve change of volume as it's distorted, and the tendency to change volume will actually depend on the void ratio. If it's loose, it will tend to contract, and if it's dense, it will tend to dilate. And of course, if you have water in the void space, then if it contracts, you'll get positive excess pore pressures, and if it's dilating, you'll get negative excess pore pressures. And this idea was latched upon by a chap called Colonel Lyman, who was the engineer of record for this dam here. This dam is Franklin Falls Dam. It's about an hour's drive north of Boston on the east coast of the United States. In those days, they called liquefaction sand flow failure. And Colonel Lyman was determined his dam was not going to liquefy. He was going to have a stable dam. And what he famously did, he arranged for a set of shear box tests, which is what you see in front of you on the slide here. And they did these shear box tests with dense sand and loose sand and medium dense sand, and you get the expected stress strain behavior in the shear box. But they focused on volume changes. And taking this idea from Reynolds, and what they found was, well, yes, a loose sand contracts, but it comes to a stable point that then deforms at constant void ratio. A dense sand will dilate, and it came to the same void ratio. And they called that the critical void ratio because that was the critical construction decision. The idea being, if the dam was compacted dense of the critical, then nothing bad could happen. At the time they came up with this idea, they were viewing the critical void ratio like a maximum void ratio in Emax or a minimum void ratio in Emin. What they rapidly discovered, this was not quite the story. This is another dam you're looking at. This is Fort Peck Dam in the United States, up near the Canadian border in Montana. And they had another liquefaction slide. This was in 1939, about the same time Franklin Falls was being built, and they applied the same ideas to this dam. What they quickly discovered was that the critical void ratio depended on the confining stress, which is what I show with the green line, and that's what today we know as the critical state locus. Today, we have got rather more sophisticated testing methods, and what I've got on here is an example of a critical state locus that we might measure in the laboratory today. I'm plotting void ratio on the left versus mean effective stress on the bottom, and horizontal stress pass. Each of that's a test, and that's a test. Each horizontal stress or state pass are undrained tests. And the original idea was use undrained tests to determine the critical state. And the circle thing there is the critical state found in that test, and the critical state found in that test. The problem with using undrained tests is that if you come out over here and you're trying to determine the critical state at this kind of void ratio, you need to start out over here. Well, our limits on our standard commercial testing apparatus is a confining stress of about 1.8 megapascals, maybe 2 megapascals. We actually cannot make or test samples at that kind of high stress with our standard equipment. If you get expensive equipment with steel jackets, you can do that, but then you get into grain crushing and other effects. But what we discovered was actually we do a loose drain test, which is the path you see here, we get actually the same result. So today we use a mixture of drained and undrained tests, and you get the same result. Now, traditionally, we fit a semi-log line to it, which is what you see here. And the slope of that line is the soil property lambda, the Greek thing, and it's subscripted by 10 to indicate it's measured on base 10 logarithms. The curved line is a little bit better fit. And there's today a lot of people like using curved lines. It's a power law relationship. So instead of having a lambda, we now have an A, B, and C. And I should mention there's a parallel property to lambda, which is the altitude or the intercept of the green line with a mean effective stress of 1 kPa, and that's the soil property gamma. And you can see the precision we get is in defining the critical state, it's about plus or minus 0.02 in terms of void ratio units. And there's a particular technique we use to do that, which is sample freezing. Provided we are careful with that sample freezing method to get or measure our void ratios, we have enormous repeatability. A couple of years ago, or 3 years ago, the University of Western Australia thought it'd be interesting to see how reliable could the critical state be measured. And what they did, they took a large quantity of tailings, and they then sieved it and sliced it and diced it and mixed it and blended it and produced a large number of identical replicate samples. And various universities and consulting firms were invited to test the samples in their own lab and submit to the University of Western Australia their estimated critical state locus. Only 8 of the labs used the freezing method. the labs who didn't use the freezing method got hopeless results. So they were all over the map. The labs that used this particular method of measuring void ratio got the results you see on the screen in front of you. Basically, it was within the accuracy of the ability to measure void ratio was the cross-lab repeatability. And I add here that some of these are university labs and some of these are standard commercial consulting labs. Now, so we got this ability to measure the critical state, and it then becomes interesting to say, okay, does this idea apply to sands? Because I've kind of given you a sort of a background suggesting it's sand related. But in fact, the early work in the UK was on clays. And what I've got on here on this slide is whatever, 12 or 15 critical slate loci. And you can see on the right-hand side, so some of these are for clays, some of these for sands, some of them for silts. Well, that's a tailing silt, that's another tailing silt. There's a sandy silt in there. This one here is from the Peck Dam failure. But the coefficients change in value, but the framework does not. The framework applies whether you're dealing with sands, silts, silty sands, or clays. The equations are the same. All that changes is the numerical value of the coefficients. Okay, so much for the critical state. I now want to switch to talking about strength. And as you know, that the early testing in our subject used the shear box, which is what you see on the left. And the figure on the bottom right is what you'll find in all our textbooks. We do shear box tests, and if we plot shear strength, we measure in the test, versus the confining stress, we get something like that. And that's the Terzaghi model of soil strength, the C-phi- model, sometimes called a Moore-Coulomb model. And the problem with that is this photograph I popped up. The Terzaghi model has this concept or an intercept which implies cohesion. But if you look at the soil you're testing and look at under a microscope, there are no bonds. If there are no bonds, you can have no cohesion because you can't transmit tension. So clearly there is a fundamental error with Terzaghi's idealization of soil strength. The chap who first pointed out this error was Don Taylor, who was a professor at MIT. And what Don did, he's looking to a shear box test. And if you do a shear box test on dense sand, you'll see the platen rise up as the sand dilates. And the thinking in the late 1940s, well, if the platen is rising up, then that platen is doing work against the confining stress. So some of the force or energy we're putting into the test to deform the sample, some of it is flowing away into work against the confining stress. So they came up with this idea, well, we must talk about energy corrections and things like that. They were driven to try and understand what they thought was the fundamental frictional behavior of soil. And you can see the basic thing here. We've got a stress strain curve, and you can see it's a dense thing, so it's dilating. And they've now plotted the evolution of volumetric strain. And what they came up with was said, well, must compensate for this work being done. In those days, they were again looking back to Reynolds, the cartoon top left, the particles get in the way of each other. And the terminology of that period was they called that interlocking. So this became known as the friction interlocking model of soil strength, where we have the mobilized strength ratio here, and it has two components. It's this interlocking component, which is doing work against the confining stress, and then we have the true friction. And notice here on this figure, at some point we get to constant volume deformation and constant friction. That's the critical state friction. Taylor describes this idea in his book of 1948, but he never gives an equation. The equation I put on the screen, the first guy to give that equation was Alan Bishop in 1950. Now, these guys are working with shear boxes, and the problem with the shear box is twofold. First off, and you see this is a standard apparatus you're familiar with, we only measure two stresses. We measure the shear stress and we measure the normal vertical stress. But there's a horizontal stress across here and there's a horizontal stress across here. So we're only measuring half the stresses on the soil. That's problem number one. Problem number two is that it's very difficult to do an undrained test in a shear box. You've got to somehow come up with a rubber membrane that doesn't get broken. So around 1940, our standard test methods changed to triaxial compression. And there, I'm sure you're all familiar with this test. But the beauty of the triaxial compression is we measure everything. When we changed, but our ideas were formed from shear boxes. So what do we do about it? Well, it's very simple. Instead of using tau of a shear box, we use the deviated stress Q. I'm sure you're all familiar with that. And instead of using the vertical confining load, we use the mean effective stress. And we use the ratio of those, which is the parameter eta here, instead of the ratio of tau over sigma. And instead of the ratio of change in volume or vertical height versus change in horizontal displacement, we use deviatoric strain and volumetric strain, and that's called the dilatancy. So there we go. Eta is that. Eta is it's the Greek letter, and that which is called the dilatancy. And how do the ideas from the shear box work in triaxial? Well, actually, they work very well. So if I now plot each one of these blue dots is a triaxial test, and this testing was done back in 1961. This is not new data. This is 50-year-old data. And I'm plotting the limiting strength now as the maximum value of Q over P, or eta max. And I plot against D min. And if the Taylor-Bishop model was perfect or correct, you'd expect that line to be at 45 degrees, and it's not. It goes up something less than that. And this parameter n was introduced by a chap called Nova in 1982, and that represents the amount of work on the sample that goes into volumetric strain rather than distortional strain. N is typically around 0.3, and it's written 1 minus n here because Nova defined n as he wanted it as a volumetric work parameter. And just like we have with our CSL, this framework applies to sands, silts, and clays. It doesn't matter what the soil type is. And you see a bunch of data on the slide here. You can see it labeled on the right, which one's a silt, which one's a sand, and which one's a clay. And the equation works whatever the soil type. Again, the M values and the N values change with changed material, but the basic equation does not. Now, we have a very good strength model, but there's an intrinsic question. If I know what D min is, or my limiting value of dilation, I can predict the strength. But where does D min come from? Why does a particular value of D min develop? To explain where D min comes from, I have to take you back to the US Army Corps of Engineers in Casa Grande. This is a figure we saw earlier, which came out of the testing at Franklin Falls. The labeling, and here we have a stress strain curve and the void ratio, and this is our critical state line. And the labeling on this figure is Casa Grande's labeling. So he labeled that plot A and that plot B and plot C. And there is an implication here that A leads to B leads to C. So somehow we observe stress strain behavior. That produces a change in volume as the material or the soil distorts. And somehow magically we come to a critical void ratio. And somehow magically that critical void ratio is unique and changes with confining stress. What we do in critical state theory is that actually Casa Grande got it wrong. He got the diagram backwards. The fundamental thing here is axiom 1, the critical state, critical void ratio locus, which is the green line here. And that's looking back to Reynolds' idea. This is a kinematic thing. And what we have with the critical void ratio is some particles are moving apart, some particles are tending to move together, and it's a birth-death process. It's a dynamic condition. And it's what is kinematically required to allow the soil to move. So we say actually with critical state theory, this idea of a critical void ratio which allows a soil to deform continuously under steady state conditions, that's fundamental. So we say actually plot C is the key first insight, and to make it absolutely clear, we call it an axiom, a fundamental tenet of our theory that a unique or critical void ratio locus exists. Now, the second idea here on this slide is that regardless of where we start, we always end up with the critical void ratio. If I wind at start loose of the void ratio, I will densify down to it. If I start dense, I will dilate to it. Well, we can express that idea very simply by saying, well, if I know what the critical void ratio is, I can define a deviation measure, and that is a state parameter. It's simply the void ratio difference from the soil's current void ratio to its critical void ratio under the current confining stress. And the idea on this slide is very simple. That deviation measure goes to zero, psi goes to zero, as the distortional strain goes to infinity. And we say that is the fundamental concept Casagrande was putting forward with his sketches. We say that's an axiom. This is the fundamental tenet of our theory, that we move to the critical void ratio with strain. Now, you can only do so much by saying, well, we have a trend. So all I have with axiom 2 is a trend. My deviation goes to zero as my strain goes to infinity. But to do something with that, we have to do a little bit of maths. There's nothing worse than looking at maths on the screen like this, so sorry. You'll find it better in the write-up. The simplest representation of that trend is the differential equation I show on the screen here now. That is, the change in the state parameter is minus, this x is actually the Greek letter chi, or Greek capital C, times the state parameter times the strain increment, the distortion strain increment. Now, you're all probably scratching your heads and saying, where does this equation come from? Every one of you knows this equation, but not in this form. Think back to when you first learnt about differential equations. Almost certainly the first equation you were taught or introduced to was the equation of radioactive decay. Well, if I called that the rate of radioactive decay and that the number of alpha particles left and that time, you would recognize this immediately as the equation of radioactive decay. This is actually a standard equation that occurs really in many physical processes, electrical circuits or whatever, where you have something tending to a known endpoint. It's actually called the first order rate equation. And we can do a little bit of mathematics around that equation. By making some substitutions and doing a bit of manipulations, you can show that that equation there is equivalent to the idea that the limiting dilation rate, d min, will be that property there times the state parameter. So we expect dilation to relate directly to the state parameter. How well does it work? Well, just to remind you, d min is the maximum slope of the volumetric strain on a triaxial test. You're looking here at a dense triaxial test. And at peak strength, we get the maximum rate of dilatancy. And that's what the data looks like. So this is the same data set we were looking at previously, but we're now plotting it in the form of the state parameter at d min versus d min itself. And as theoretically predicted, you get a linear relationship. And does this work for all soils? Just like the strength model and the critical state locus? Yes, it works all soils. Here you have a bunch of data on silts, sands, sand again, clays in here, clays in there, silt in there, and there's another silt. Yes, the value of this chi changes from one soil to the next, but for any soil it is constant. Okay. We've got to move on and ask ourselves what happens before peak strength. Well, this idea of D, we looked at the peak value before, but you can also take it as a slope anywhere on this curve. What I'm plotting here is the dilatancy D, which is just the slope on the triaxial test, versus the mobilized stress ratio eta. And what you see is a very simple relationship. Eta equals m minus d, and m is simply the intercept as you cross the zero axis here. Now, this includes both elastic and plastic bits. You'll notice something funny is going on here. That's just pure elastic bits. Now, when we do engineering calculations, it always involves a stress strain curve. And you're going to say, well, I do limit equilibrium calculations for calculator factor safety. There's no stress strain curve in that. Well, actually there is. because limit equilibrium is based on the idea of rigid, perfectly plastic deformation. If you've got no, when things start moving, everything just slips, and it slips at constant stress. If it hasn't started slipping, there's no deformation. So you have a rigid plastic idealization, even though you may not be aware of it. And this is true of every one of our engineering methods of assessing strength or stability of a structure or soil. It always involves a stress strain model somewhere in it. So I say, well, okay, as we proceed forward, we're going to want to work these strength ideas to work out how this may affect how soil behaves. What I've got on here on the screen here is just a stress strain curve. So they are measuring stress up that way and that strain down that way. What I want you to notice is if I start loading up here and I'll go across to there and I unload, I don't get most of the deformation back. Most of the deformation is permanent. The stuff that's permanent, the terminology is we call that the plastic deformation, and that is the elastic. And we break any strain into this equation here. It's broken simply linearly into two components. Formally, that is known as elastic plastic strain decomposition. What I also want you to notice that we actually start accumulating plastic strain here with Y. Y indicates a yield point. As we start yielding and we get plastic strain, the material can change its strength. So yielding is not something that necessarily has to just run horizontally. You're actually allowed to increase or indeed decrease strength as yielding develops. The mathematics or the physics around this very obvious behavior. Any of you can go and do a track seal test or a shear box test, and you'll observe exactly this behavior. It's not anything magical I'm just putting on the screen here. The guy who first put the ideas or formalized the ideas into a mathematical framework was a chap called Tresca, and you see the date 1864. These ideas have been around a long time, and to capture this behavior, you always require three things. You require a yield surface, which is where does the stress state where plastic strains start developing. You have a hardening law, which tells you as you do or as plastic strains occur, how the yield surface changes size or shape. And the flow rule just tells you how much of the strain is going north-south, how much of the strain is going east-west, and how much of the strain is going up and down. It just tells you which way everything is moving. And you always have these three elements, whether you're doing this for aluminum or polyethylene or sand or clay. You always have these three elements. So what does plasticity for soils look like? This is critical state theory. And this is critical state theory on one slide, and I'm going to take you through it now. I put bottom right Casagrande's cartoon or schematic, because that is we're putting mathematics around this idea. And the first thing we're going to do is we're going to make void ratio explicit. So we're going to have our critical state locus, which is top right. So the green line is my critical state locus. And I have deliberately drawn this as curved just to reinforce the point we do not have to have a semi-log line for this framework to work. Over here, I have got a QP plot. But if you look carefully at my axes, I've also labeled it distortional strain increment and plastic volumetric strain increment. So you have in front of you, if you will, what is two graphs laid on top of each other, where we're plotting strains and we're plotting stresses. And the reason we do that is here. If I'm sitting at a stress state on the PQ plot of this, then I can say, okay, what is the amount of volumetric strain and what is the amount of distortional strain? So that vector there represents the proportion of volumetric to distortional strain. That vector comes from my stress latency relationship. Now, the neat thing is there is a theorem, and the reason we're doing this, and I don't mean a theory, I mean a mathematically proved theorem, the second law of thermodynamics. If we have made the right choices of stress and strain measures, the yield surface will be perpendicular to that vector. So I can, I want to go back, sorry. If I know what my gradient is here, I can then integrate that gradient, and that is where this bullet shape comes from. The bullet shape is the yield surface, and I've got it by relying on that theorem, just deriving it. So this is not based on experiments. This is based on the second law of thermodynamics. When you do an integration, of course, you get an integration coefficient. And that orange dot represents the chosen integration coefficient. And what critical state theory says is, well, we know the green thing is my critical state, because for any given void ratio, or I've got a P dash, and the P dash tells you where that is. And all axiom 2 is that orange dot must move to green dot with shear strain. Now, the green dot may evolve as the void ratio evolves. That green point will move along the line with the slope of m, and the yield surface will evolve as the orange dot moves to the green thing. How the orange moves to the green, that's our hardening law. And it's just a simple linear equation. Now, there is a little catch in here. Remember, we had a maximum delatency of chi psi. And our vector, or strain increment vector, is perpendicular to the yield surface. That means if I went over here, I could have more than my allowed amount of dilation. We chop that off by putting an internal cap on it. And that's from mathematical self-consistency arguments. And that's it. That is critical state theory on one slide. That's the basic ideas. Oh yeah, and that's my limiting dilation. Sorry, I got ahead of it. What does it look like in terms of equations? Well, it looks like this. They're very simple equations. Nothing magic in here at all. If there's any catch, it's they have to be solved simultaneously, which is why we do it numerically. But each element of the theory is verging on trivial. And the point I popped up here in pink is these ideas are not new. This idea of stress latency is 70 years old. The integration of stress latency to form that derived yield surface with the bullet-like cap, which is this equation here, the basic theorem was derived in 1954, and that was used by Schofield and Roth in 68 to derive the bullet. The hardening law is a bit of a longer story. It's implicit in Casa Grande, but it wasn't cleaned up until some work in the Arctic in 1990, and you'll see that in a moment. But that's 30 years ago. The properties involved, I've introduced them to you as I've been talking through them. They are very simple properties and easily understood. The only one I haven't talked about yet is H, which is the plastic hardening modulus. And H, you can think of as the initial stiffness in a triaxial test. We actually use it in a slightly different form, but it's good enough for understanding to think of it as the initial stiffness here. What you're looking at is a calibration of this critical state theory to data. So brown is a dense triaxial test on sand, which is dilating rather strongly. And blue is the fit of the theory, the calibration to that test. And on the right here, I've got the void ratio plot. And note we've got absolute perfect honoring of the evolution of void ratio. Now, as a principle, if you think, I'm showing you so far drain tests, and it's a principle that if you look at a triaxial cell, which is what you've got on the screen here, that the thing I've circled in blue at the bottom is the drainage valve. And you closing or opening that drainage valve cannot change soil properties. That is a fundamental principle of our business. So the question is, okay, we think we understand soil. What happens if I numerically shut the drainage valve? And we get this. This is, again, the brown is the data. It's a strongly liquefying test, one of the more extreme tests I've got in my database. And blue is the fit of the theory to that test using a calibration from dense drain behavior. And we're coming to later, we're going to talk about undrained strength. Just notice we have a perfect fit on undrained strength, peak undrained strength. Now, what I've taught to you so far is very much a laboratory presentation. It's a laboratory presentation in the sense that it assumes you know or you can easily measure void ratio. But when we go from the laboratory to practical engineering, you've got to say, okay, how on earth are we going to measure void ratio in real fills, and what we're going to do? What you're looking at on this slide is the north coast of Canada. Get rid of that. On the left, we have Alaska. On the right, we have the Yukon Territory and Northwest Territory of Canada, and yellow is the dividing line between the United States and Canada in this part of the world. I've annotated up here Prudhoe Bay. It's off the screen. It's in Alaska, and Prudhoe Bay is one of the world's giant oil fields. It's provided about a quarter of the oil of the United States for something like 30 years. It's an enormous resource, and the geology of that oil-bearing formation in the Devonian extends across into Canada. And in the 1980s, the Canadian government encouraged oil companies to explore for oil in the Canadian shelf. So we were going to explore for oil over here. And the perception was, yes, they had a vast reserves of oil in Prudhoe Bay. Canada had several times that over here. To give you a fix of where we are, the jumping off point was a town of Tuktoyaktuk, which is there, and that's what Tuk looks like. And we're a 4-hour flight on a 737 from one of the more northerly cities in Canada. So we're actually well inside the Arctic Circle. And I was a supervising engineer for Gulf Canada Resources, and our acreage was pretty much where I'm indicating here. And what does it look like? Well, this is what it looks like 9 months of the year. This photograph is taken 75 kilometers offshore. What you can see from the shadow is that's a helicopter. We've flown out and landed on the ice, and that's one of my colleagues who's just walked down to look at an ice feature. And you can see these are quite large pieces, and you can see from the scale of it, it goes everywhere. And it moves. Now, this is not a badly designed ship. This is my exploration platform, the Gulf Moloch Pack. To give you a feeling for scale, she is about 100 meters across on the waterline. And when ice moves, it crushes. And when it crushes, it doesn't do it as a smooth process. It produces large horizontal loads and large vibrating horizontal loads. So how did we set about resisting those loads? And obviously, you can't use a drill ship in these conditions. In essence, this structure is a large shear box. You see the cutaway here. We fill the inner core with hydraulically placed sand. And this is an exploration structure. So we're going to move it from site to site, but it's a steel box. It's got a fixed set down depth. So we actually also have to build a sand structure underneath it. We call those sand berms. The seabed is usually quite weak, so we cut it out and we then infill it with sand, and that's what our structure looks like. Now, this is how we built the things. You see, I'm bringing my dredge onto my location, and I'm standing or taking this photograph from the survey vessel. That's the rail of the survey vessel, and you see how closely we operate them. And here we are 5 minutes later. Now, in mining, you're used to 200-ton dump trucks. Well, this is my 6,000-ton dump truck. And how do we control this operation? Well, this photograph here is taken on the bridge up here, and it's taken from the helmsman's position. This is in pre-GPS days, so we have we've set up radio ranging systems for positioning the ship. So the orange box is the position fixing system, system called Solidus. This here is the computer, and the computer has been loaded with my design drawings. And the computer is also interfaced to the position fixing unit, and it's interfaced to the ship's gyro, so it knows which way the ship is heading. And the computer generates a video game over here for the helmsman. So we show a green box where we want the ship to go, and we give the helmsman a yellow cartoon of a ship, and their job is simply to maneuver the ship into the green box, and then we drop the sand into place. And this is an example. This is taken from the computer screen. That is the design drawing in white, and that is 2 survey lines across the structure showing how we're doing. Bear in mind, this is in 20 meters of water. Nobody has ever seen by human eye what one of these structures looks like. It's always done by remote sensing. Now, I've mentioned hydraulic fills. I've mentioned hydraulic fills liquefy in the early part of the talk. And I've mentioned that we have large cyclic loads, which we know will possibly cause liquefaction. So I am one paranoid engineer of record. So what am I going to do? Well, it's very simple. I look to Colonel Lyman and the Corps of Engineers for my inspiration. I say, well, I'm going to use as my decision criterion the same criterion as Lyman. I want material to be dense of the critical state. Or in terms of state parameter terms, it's very simply, we just want state parameter less than 0. Now, what I have that Colonel Lyman didn't have was modern electronic penetration tests. I'm with an oil company. We can have equipment made to our specifications. So this is one of the first probably the first digital CPT with downhole analog to digital conversion. And the chap you see in front of you is the electronic engineer who designed it for us. The stuff is still in production. It's made by Geotech AB in Sweden. And what we do, we do a lot of probings of our berms before we set the structure down. And when the structure has been landed and we infill the core, we then also test the core. By measuring tip resistance, right, so what you measure with the CPT, how do we relate that to the critical state and my decision criterion? Well, what we do is this. We construct a large tank, which is effectively a large traxor cell, and this one's 1.2 meter diameter. We place into that 2 tons of sand, and we then stress it up. It's like a traxor cell. I can load it, stress it horizontally, and I can stress it vertically. And we then, when it's stretched to the desired stress level, we push a standard CPT into the tank. And we measure tip resistance like this. And we also measure side friction and lateral stress, but we're interested in the tip resistance. And then we finish the test. We excavate the material carefully, and we use a nuclear density logger. So we can actually measure the void ratio after the test to say, okay, at this depth, we have this void ratio. And we then associate that tip resistance with that void ratio. Now, we can plot the whole thing up. We're now plotting up each of these points here is a test in the tank. Okay, and they're actually negative things because what we've done is we've measured the critical state of our sands. We've got a critical state locker. So if I know my confining stress on my test, I know my void ratio of my test, and I know the critical void ratio, I can simply compute the state parameter for each of those tests. I can plot state parameter versus tip resistance versus confining stress. And what you find is the data plots as simple radial lines. Now, the slope of the radial line is just the normalized penetration resistance Q. So we then just say, okay, let's just plot Q versus the state parameter, and you get this very simple exponential relationship. And that's the basic test, because I'm now in a position of being like, well, better than Colonel Lyman. I can do my CPT, I can go to this relationship, and I can say, okay, what's my state parameter? If I've measured whatever, what's that say, a normalized tip resistance of 100, bingo down, I've got a state parameter of about, I don't know, minus 0.13. I'm a happy guy. However, there's a problem. If we go and look at the world, various people have done this sort of calibration chamber testing. And you always get the semi-log relationship, or very close to it. But the relationship differs from one sand to another. This has been known since at least 1986. People usually say, well, it's sand compressibility that's affecting things. It's actually not just compressibility, but for the simplicity, that's good enough idea. And the problem is simply this. If we, for example, measure a normalized penetration resistance of 70, which is what I show with the red line, if the appropriate calibration is this brown line, which is Reed Bedford sand, then my inferred state parameter is minus 0.14. I am one very happy engineer of record. Conversely, if Toyura sand is a better match to my material, then my state parameter in situ is about minus 0.03, which is getting me into near flow liquefaction potential. And the problem as an engineer of record is my decision on whether it's adequate or inadequate depends not what I measure with the tip, with the cone, that's the red line. It measures on what is the appropriate calibration. Now, I actually had the luxury of testing my sand in the chamber, but going forward as engineers, we do less of this testing in chambers than you might expect. It's better to understand why this relationship is changing. So that's where we went next. We said we need to understand why the CPT gives a different trend as the material changes. And the way we did that is we used cavity expansion theory. And the idea of cavity expansion theory, and this is a theory which was originally developed for testing of metals, and which was picked up by the soil mechanics people. And you notice my diagram says pile. This is the standard theory for our end bearing of pile design. And it's just say that the tip resistance, whether it's a pile or a CPT, is some scale factor times the limit pressure. And the limit pressure is the idea we can expand a cavity. And if you take a cavity here, which is the blue hole, and you magically increase the internal pressure so it expands, the relationship between cavity pressure and cavity displacement will show a trend like this. You come to a limiting pressure, and that is called the cavity limit pressure, or P limit, and we say that the tip resistance is related to that by a simple scale factor. So we did that. We put the theory together using critical state theory, and this is the result we got. And we're looking at here data from Ticino sand, which is one of the most comprehensive data sets. And this was testing done in Italy, and for each of these dots is a test where they have reported a value of void ratio, and they've reported a value of confining stress, and they've then reported the measured representative tip resistance. We obtained a sample of Ticino sand, and we determined its critical state lockers, so we converted their void ratios into state parameters, and that is how their data plots. We then took those E0, P0 pairs and put them into North sand for the cavity expansion for this, and we get that. And then this CQ factor is simply the ratio of that to that. And that's all very nice. Oop, gone the wrong way. And we then went further and said, actually, we need to check this idea works universally. And this was done by Mason Gafgazi, who's now a professor at University of Toronto. And he looked at the world database, and he came up with 331 calibration tests, which is what you see on the screen in front of you. And he took there, and we obtained critical state loci for each of the sands tested, so we can convert the E0s into a state parameter. So we said, okay, the people doing this calibration testing, we're going to say they've given us the truth. They've measured an E0 and a P0, and we've turned it into a state parameter. So that's a state parameter measured. They have reported for that state parameter a tip resistance QT, so we can take that QT, stick it into our calculation method with the finite elements, and we can compute a state parameter. So this is computed, so this is a complete test of the process. And this plot compares truth with what we compute, and you can see there's absolutely no bias, and the data tracks dead on trend line. Now, the scatter is plus or minus 0.04, which is, you might think that's a little disappointing. What I want to draw your attention to is this. This is test E139 at Ticino sand, and that's 169. And they have identical reported void ratios and identical reported confining stress, but they differ in their reported tip resistance by a factor of 2. And really, this reflects the ability to accurately measure void ratio. Bear in mind, we're dealing with 2 tons of sand, or best part of, in each of these tests. Also, some of these tests do not show as clean a QC value as the one I showed you earlier. Sometimes there's a bit of ambiguity over that. So in my view, I'm showing you here the data at face value as reported in Geotechnique. My value is that, or my judgment is that most of this scatter is due to testing repeatability. We move from a sands to silt, the same methodology applies. And we get a similar relationship, except we now have to incorporate the pore pressure. So instead of using Q, it becomes Q times 1 minus BQ, where BQ is normalized pore pressure coefficient plus 1. And we have no chamber tests on silts, or as yet we don't. So you might say, well, okay, how does this work? Well, what you're looking at here is the Peck Dam failure. And they put CPT down in the soil that subsequently liquefied a year before liquefaction failure. and that's the blue line here. As the board of inquiry into this failure, we took the methodology I've just described to you and processed the CPT data, and we said that is our assessed state parameter in the tailings, which is the green dots. We then discovered that the engineer of record had carried out very high quality tube samples prior to the board being involved, and they had actually, bless them, measured the density of those tube samples at the site before they were moved. We had looked at the tailings, and we come up with the idea there was a predominant tailings, which in this tailings mass, and there was slightly sandier stringers in it. Now, we did not know what each tube contained, but we said it could either be all of the predominant material, or it could be all of the sandy material, or it could be something in between. So what these bars show here are the state parameters based on the engineer of records quoted density for the tube, and then assessing it whether it's full of the predominant material or the more sandy material. So that then becomes our reference point. And as you can see, the process validates very nicely indeed. Okay, so far I've given you the methodology. Let me share how this whole thing works. This whole business, the drain to undrained transition, we're all familiar now that these things fail usually with no warning whatsoever piezometrically, and they fail in a matter of seconds. So why is this happening? To understand why it happens, you need to take soil loadings 2 steps, and it doesn't matter what your path you're imposing. You can always say, perhaps I will instantaneously apply an undrained load, and I will then let some time elapse before I put on my next undrained step. So I'm going to be loading the soil in these 2-step manner. And the drain condition is not that we have zero excess pore water pressure measured in the piezometer, it's that the rate of drainage, du dt, which is the pink, is greater than the rate at which pore pressure is created, the du dt in blue. Bottom here is the Skempton equation for excess pore pressure. And I put it down here. I want you to notice there are 2 terms. This first term here is the excess pore pressure created by confining stress. You double the confining stress, you'll get an increase in pore pressure because it hasn't had time to drain. That's just a confining stress effect. This term here represents the amount of pore pressure generated by the particles tending to distort or move over each other. And the problem we have is if you're doing consolidation analysis or a large deformation consolidation analysis, you're only concerned with this term. You're not asking, what about this term? So the issue is, how fast is pore pressure being created compared to the rate of drainage? To give you an example of the rate of drainage, you can actually calculate it by Terzaghi theory, but people tend not to do that for sandy material. So here's some raw data. We had one of my ice loading events, which is coming in here there in the arrow, and it produced some excess pore pressures locally in the Molecular pack, which show here. And this is my measured pore pressure data, and the blue is that transducer there. Now, this was actually measured in 1986, and in 1986, a 15 megabyte hard drive was an extremely large one, which cost Gulf Oil a lot of money to get our hands on. So our data acquisition strategy, so we could see the details of what was going on, we did what we call burst files. We had a high scan rate file. We could only have it for 90 seconds, but we used up our storage because I actually had 600 transducers on the rig. So what you're looking at here is a burst file here, and then we sequence them. We change the trigger point. So as we didn't want to sort of run them off 5 in a quick go, and that used up all our storage. So every time we triggered it, we raised the trigger threshold. So we have one file here. There's actually 2 back-to-back here because it kept going on. So even though we raised the trigger point, it just gave us a second one, and then it all stabilized, and we got the thing over here. What I want you to observe is that the T50 was 5 minutes. Now this is a clean sand, about as clean a sand as you'll find, and the drainage path is 10 meters. So that gives you 5 minutes by direct measurement. Okay, let's now talk about the rate at which pore pressure is going to be created. What you're looking at here is a QP plot on this side, and here's the corresponding stress strain curve. And this is just a simple undrained test on a loose sample, which shows liquefaction, and it comes down to that. Now I can impose a little bit of drain loading, which I've done here, and I've taken up to that stress state there. And I now impose an undrained step. And notice I've got a reserve of undrained strength. So even though I've gone to put a bit of a small perturbation or a small undrained load on, nothing bad's necessarily going to happen. But what happens if I put a bit more on? I'll take it there. When I put my undrained step on, I have an instantaneous loss of strength. That actually is a negative modulus, and we call the stress condition which starts as negative modulus happening, we call the instability locus. Now, when that happens, that element has to shed load to its neighbor. If its neighbor is also above its instability locus, it will also have to shed load, and you'll get a propagating wave. So let me show you what that propagating wave looks like. This now is the first of my examples. This is the Tar Island Dike. This is actually a tailings dam. It's in northern Alberta. It's an oil sand tailings thing. And you can see it on the left-hand side. This is pretty much at its final height of 100 meters. And that's the Athabasca River there, and that's our tailings pond over here. This is about 30 years earlier during the initial stage of construction. And what we have is a compacted cell, and then we spigot from that into beach above water, and there's a retaining pond. And if you look at it in cross-section, it's standard upstream construction. We start out with our starter dike, and then we switch upstream where we're going in lifts, and you can see them there. When they were developing this, they actually had a number of subsidence events as they were learning how fast they could raise. And, these were not dam threatening. There were substances or liquefaction slips into the tailings pond. And this is how the guys learned to do the construction or come up with the construction method. What's interesting for our purposes about this is a very simple static loading. We're doing just it's almost like it is a dead load test. There are no funny foundation movements. There's nothing odd going on. This is the largest slump I'm going to show you. And they built it from, you should see the dates here, May the 14th through to August the 22nd. When the slump occurred, it dropped about 5 meters. This is from the engineer of record, his notebook of what the slump looked like. Okay, now, and it happened rapidly, so it's a liquefaction slump. This is 4 CPTs from that impoundment. We don't have CPTs from the time because that was before we had CPTs in Western Canada. However, they continued building the dike in the same way with the same construction techniques, using the same material. So this is as close as we can get to what we believe would have been in place. It's the same material just 20 years later. And you're looking at 4 CPT soundings. And here is the tailing surface. Comes down like that. And this is my upstream step out. So this is my top of my cell, which is in here. So this is compacted material. That is the water table. It drops down because we have engineered drainage. And what you can see is very variable. How are you going to pick a representative state parameter from that? Well, I have to take you back to the Molecular pack. What we did in the Molecular pack, we did some fairly intensive CPT probing. So the inside of the core, remember rightly, it's about 80 meters across inside. I think it's probably more like 74. And we put in something like 38 CPTs on a closely spaced grid. And if you take that transect there, these CPTs look like this. So you can see a traceability of a denser zone, and you can see a traceability of a looser zone, but you see they come in and out, and they fade away. Well, what we did was we said, actually, this can be converted into a computer, into what we call a geostatistical representation. And this is 2 of those geostatistical representations. So what you're looking at is a slice through the sand core. Black is denser or more negative state parameter. White is looser state parameters. Both of those diagrams faithfully gives the standard deviation and the mean values of the CPTs. So we've got an accurate representation, but we have to allow for the variability or the stochastic variability. And what we've done is put that into a computer. So we've then said, okay, well, there's our representation of the Molecular core, and we can run an earthquake at it. And you're now looking at contours of excess pore pressure ratio, or an RU value, under the standard earthquake. So each of these runs here is a computer run, and each of them has got the same earthquake, but each of those has got a different slice like that. So I'm, whoops, going too far there. So I've got, say that's realization 1, that belongs in here. That one there is realization 2. So you get the idea, and we've done it 6 times. And you can see the pattern of excess pore pressure, even though it's exactly the same earthquake, varies a bit depending on the details of the layering. Even with our CPTs at 9 meter centers, I cannot say I've got it exactly nailed down. Now, you know, when we do our calculations, engineering calculations, it's very rare to have this level of detail. You know, I had an unusual amount of CPT data I could do it. Generally, you won't have anything like enough data to create a stochastic model. So what we do in our engineering calculations, we take a representative value. So we're going to say, okay, you know, do we take the average state parameter from here? Would that be sufficient? Well, if you use the average state parameter, you get no excess pore pressure computed. If you use the 50 percentile, so half the sand is looser and half the sand is denser than your value using your calculation, you get a hint of it. And you have to progressively go looser and looser to get something that looks like reality. And when we get so that 80% of the sand is actually denser than the value we use, we get this picture here, which is my personal preferred choice as perhaps the best engineering match to that. If we go to the 90 percentile, so 90% of the material is denser than which we pick as for our calculation, I think that's too conservative. I should add here, I haven't got time in this talk to show you the stuff, but they did something similar for the Oosterschelde barrier offshore the Netherlands, the flood defense works, and they did it by centrifuge testing, putting little pockets of loose material in the models, and their preferred number in Oosterschelde was a 90 percentile. Now, taking that knowledge, we can go through to our dike, and this is the dots are the 4 CPTs I showed you before, processed using the methodology that validated at CADIA, which then spits out a state parameter. I've flagged here on the right-hand side, I say, well, that's my beach above water. I've got a transition region. That's my beach below water, or my predominant deposit. I seem to have a relic subaerial exposed beach down here, and then I've got more beach or submerged beach above water. And the black lines are my pick for characteristic values. So bear in mind the rule is 80 to 9%. You could, I suppose, do it formally by processing the data and in box counting. But when you look at this kind of scatter and you've got to call off where you think the transition region is, I prefer to do it by engineering judgment. And the black lines are my engineering judgment. You may differ, your judgment may differ from me. I'm going to come back to this later. You'll notice this line is not quite at 0.06. It's actually at 0.065. But it struck us at the time when we were doing this, so, are we kidding ourselves? We've got third decimal place precision in this process. So we actually put 0.06 into the finite element model. So here is the finite element model of the slump I showed you earlier, or the slump I told you about earlier. What you're going to see when we construct the model, you'll see it being constructed in the video. You'll see them putting the layers in. And when we get to the final lift, you'll see it flip undrained. The contours over here, the color coding, is the stress ratio eta divided by m. And we do that because when you go to 3D, m changes to the intermediate principal stress. So if you use this ratio, everything looks after you. When you go to red, you're in the critical state. Okay, so when you hit red, it's gone critical, and you'll watch the propagation. So let's run the video. Now, notice we have got this lovely settlement. This is the first run that was done. So this is I'm honestly reporting to you here, the the judgment process we went through to run the simulation. We actually calculated 4 meters of settlement. That's where I regret that third decimal point, because if we'd gone with 0.065, we'd have nailed the actual 5 meters on the first pass. The propagation velocity is about 50 meters per second. So, I don't have a time base on this to show you. And at the instant of failure, there is zero, nada, rien, excess pore pressure. So it goes from snaps from drain to undrained and then propagates at 50 meters a second. And that is critical state theory at its best. Now, second example, I introduced you the yield surface, which is what you see in blue. This is a QP plot. And I told you about this internal cap, and that the internal cap came about from considerations of mathematical self-consistency. A reasonable thing was, you might say, well, Mike, that's contrived. That's just an artifact. So let's do some tests to see whether it actually exists. So what you're looking at here is a lab test where we've loaded it drained up here to establish the yield surface, and we're then tracking across decreasing the confining stress and decreasing the Q. We decrease both together because it enables you to see the elastic shear recovery. Some people, when they do this, they call it constant shear drained and they go dead horizontal. I was more interested in getting down into the yield surface down here, so it's more convenient to come down at an angle. Plus, I can actually see the way the elastic strain recovers. When you cross the cap, you have to stay on the cap. So the yield surface then has to shrink. So as you keep loading through to here, the yield surface shrinks, and the stress state stays on the yield surface, and then you get the stress state eventually moves up to that vertex. So we're down here. I'm nowhere near this sharp vertex point. When I get to point C, I hit the vertex. Okay, so let's see what data looks like. Okay, what you're looking at here in black is the measured data in the traxial test on the path. So you can see the path coming down. There's my point A when we hit the cap. Point C is when we hit the vertex. And you look at the behavior here, and you look at the volumetric behavior here, and it all takes off. So the cap is real, and it's important. And this stress path is important because this stress path is the cause of the Aberfan failure, which is the thing you see on here. And there was a school down here. Not quite as bad as your last failure, but very close to it. And that moved at 20 kilometers an hour, the speed of the flow slide. And this constant shear drain loading is implicated in the failures of many tailings dams. Most of what our liquefaction case history is liquefaction is really secondary. There's been something else going on. And basal yielding has much the same stress path as the constant shear drain I've just shown you. So Fort Peck, that was a failing foundation that caused liquefaction slide. Aberfan's one I've just shown you, that was actually generally increase in pore pressure. What happened there, the tailings impoundment was on top of a spring, and they had a large amount of rainfall, and the water pressure in the spring came up and down the dam came. Nerlock was a foundation failure. They built it over soft clay. Fondao, you know about that. You've seen the board report. Cadia was a failing foundation. Now, I've shown you some fancy analysis using finite elements. The universal reaction when you present other consulting engineers with this and say, chaps, we've got to use finite elements, is why can't we just use undrained strengths, Mike? And standard limit equilibrium analysis. Well, have a look at this. This is the undrained strength at the instant of failure. So we're going to analyze. Can I back up? We could analyze this failure here by saying, okay, let me put a slip circle analysis through it, and let me put a value of SU for this material in that slip circle analysis at the height of which failure develops at. And we'll call that, calling that a yield strength. I'm sure every one of you, certainly those of you in Brazil, are well familiar with this plot on the left-hand side because we correlate. They've looked at case histories of failures, and they've back analyzed them and got a value of SU, and they plot it versus vertical effective stress before failure, which is a standard thing to do, and they've related to tip resistance. Over on the right is my colleague Ken Bean. He assembled something like 300 undrained triaxial tests, and we plotted all his data up there. And I plot it in exactly the same strength ratio, except I'm normalizing it by the state parameter. And you see exactly the same range. It's something like, regardless of how loose your material is, you're unlikely to get a strength ratio less than about 0.18. And it will then climb up to, at a state parameter of around 0, you're up about 0.35. And the same numbers are here, but they don't know it's a state parameter because they're working to CPT. Now, remember this plot? Remember I pointed out how accurate we were there? The obvious question is, okay, Mike, what's going on? Why do we have the scatter here, and yet you're telling me we've got perfection here? Well, the answer is simple. There are actually 3 unmeasured parameters. All they're inputting here is tip resistance. All we're inputting over here is a state parameter. But we know that the critical friction ratio, the plastic hardening, which you can also think of as the slope of the critical state line, and the elastic bulk modulus all control the behavior. The reason I get perfection here is I'm using the correct value of the elastic modulus, and I'm using the correct value of plastic hardening, and I'm using the correct value of M. Over here, this data, they don't know what the value of M is, they don't know what the value of lambda is, and they don't know what the value of K is. So this isn't just random scatter, it's actually unmeasured parameters. And that's why I don't like undrained strengths, or at least by undrained strengths from an effective stress basis, because you're just deluding yourself. If you look here, I'm looking at the state parameter here. I can have a strength that goes from 0.18 to 0.33 at constant state parameter, purely because of the change of H or K. You're deluding yourself that you actually know anything if you're working with undrained strengths. Okay, further extension, residual soils. This is the Cadia foundation. The brown line is the stress strain curve measured at one of the triaxial tests on the Cadia foundation which triggered the liquefaction. And this is the stress path over here. And I've drawn in green through the end of the stress path the critical state friction ratio, or the final friction ratio. And remember the stress to latency relationship, dP equals m minus eta. Well, if you look at the data here, it is showing contractive strain because the stress path is bending to the left. If it's bending to the left, then dP is positive. But eta, you can see, is above the green line. So clearly something unusual is going on. Blue is what we've done with Norsan. How did I get Norsan to do that? Very simple. I've looked at their stress to latency data and I said, actually, what I've got is a material which shows a particular value of M to a threshold strain. Once we take this residual soil beyond its threshold strain, the material starts degrading. And that was the degradation curve I used to get that match to the data. So critical state is it's based on rigid particles. That's the derivations I gave you. It's based on particles that don't degrade. But we can deal with more complicated soils, structured and bonded soils. We can allow M to evolve. There are some restrictions on how it can evolve, but we can add that in. We can add in crushing soil particles. The starting analogy from Reynolds was steel ball bearings. Well, what happens if they're squashy marshmallows? And we certainly can have the critical state line or lockers evolving with strain. And we've seen that in a number of occasions. If you've got particles breaking, the gradation changes, so the critical state changes. But again, you can add that detail in. And we've also got creep. M may depend on time or strain rate. And more important, this P image, remember my orange dot that moved to the green dot? Well, that can also be made a function of time if you've got a viscous model. You can add these features in. So it's not the end of critical state theory. And the way, when you look into new material, and this is going to apply to some of you guys in Brazil, you process the data to stress the latency form to see what the real material behavior is. We can then say, okay, what other features do we need to add? So summary, I'm pretty well at the end now, I'm hopefully not too badly on time. Critical state theory is not new. It's been developed 1935 to 1990 with many contributions from many workers. The properties, I've described them to you. I hope you agree they're easily understood and familiar. And this sudden drain to undrained instability is intrinsic to the theory. It's built right in. You don't have to add anything or invent metastable collapse or anything. It's right there from the get-go. The CPT remains the key in situ test, but you've got to process it properly. You've got to allow for the soil properties in the processing. You don't use a universal correlation, and please do not use QC1N. That's not the way forward. You may need to consider soil structure, creep, and particle crushing. But it's simple to check, and it's not that difficult to add in. And the analysis of what you need is implemented in modern software. All the major vendors, Plaxis, FLAC, RS2, and Sigma W, they have all provided Norsand now. And the simulation I showed you of Tar Island, that was actually run with Plaxis. So it was commercial software, not research software. One of the things that drives me is I don't believe as engineers we should be using black boxes. So I am fairly insistent that everything should be available to people who wish to dig deeper to check on things. So all the data produced by Gulf is public domain. So in essence, this talk is brought to you by Gulf Canada Resources. It was the Gulf shareholder money that got the show on the road. And all the data supporting this talk is public domain. With Traxio data, cyclic direct simple shear data, the CPT chamber data, and the field data, say we want to look at the field data. Not only that, the Traxio and the CPT processing programs are public domain. The open source code, there are no black boxes. You can look inside it, you can see the code for yourself if you wish to. You know, most people just run the executable, but in principle, if you want to look into it and say, how is this made to work? It's there for you to inspect. In terms of finite element modeling, what we have in the public domain, which you can look at the source code, is Norsand has been implemented in the University of Manchester code. If you there's a famous textbook, Programming the Finite Element Method, by Ian Smith and Vaughan Griffiths. I think it's now in something like the 6th edition. That textbook is accompanied by a vast amount of public domain finite element code. Norsand was put into that code by Dawn Shuttle, and that has been published. You can see the algorithm. Imperial are now also whacking Norsand into their thing, and Imperial are very insistent on making their algorithms clear. Because the objection with people like FLAC or Plaxis is we can't actually see inside how they're making the thing compute. So Plaxis and RS2 are proprietary, but you can verify it, and they verify against the standard stuff very nicely indeed. FLAC is slightly different because FLAC you can actually have the source code as a user-defined model. So that is public domain. But FLAC have also got their own version of it, which is proprietary, but they give much the same result. Now, what I want to leave you with is this. What I've shown you tonight is probably new to a lot of you, which is why you wanted this talk. But every one of you will have, as part of your education, gone through or been educated in the Terzaghi consolidation theory, which is what I've got on the screen here now. And that theory is a second-order partial differential equation. If you lose this term over here, if you've got constant total confining stress, it's actually the diffusion equation. What I've shown you this evening is critical state theory, and the key equation in it is this one here. That is a first-order ordinary differential equation. Mathematically, it is simpler than Terzaghi consolidation. So if you can learn Terzaghi consolidation as part of your geotechnical education, every one of you can learn critical state theory. It's actually easier. So that's the end of the talk. I hope I caught your interest. I'll take your questions if we have time. Over to you, Fernando.
Okay. Mike, this was a remarkable lecture going through basic critical state concepts and then bringing as expected, bridging as expecting theory and practices, stressing the need for rational approaches, everything that we do believe and we are trying to pursue. So I hope that you have enjoyed and benefited from this presentation, as much as I did tonight. As I have mentioned, the lecture will be written. We'll have a written version of this lecture that will be published as a paper, as a special paper at Soils and Rocks. So all of us can go to this written version and sort of review what has been discussed tonight by Mike. And there will be written questions that we have received throughout the presentation. And I think that these will be answered by Mike later on. I can send you the questions and you have personal replies from him. Mike, thanks once again for accepting our invitation. We hope to see you here in Brazil. We hope to have the opportunity of hosting you here in Brazil for a personal face-to-face talk after this COVID has ended and allow us to get together again. So thanks a lot for accepting our invitation and the generosity for going through all the information, all the concepts that you have gone. Thanks a lot for all those that have shared this experience with us tonight, and I hope to see you all in the near future. Good night.
Good night. Thank you, guys. And I look forward to the beer.
Absolutely, absolutely. You've got to try Brazilian wine as well.
Sounds a plan to me.
Absolutely, absolutely.
All right. Good night, guys.
Good night.